Hello, it's Keith here, and this is lesson 97 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at MaxTile, which is my software multi-platform tile map. It's on the Spectrum Next today. So here is the example here. We're using the 256 color mode and 256 color tiles, which means each tile uses a total of 64 bytes, which is an awful lot. I say that because there is an alternative version we'll see next time, which uses 4 colors per tile, and then it adds a sort of tint, which gives a kind of Game Boy effect, which I actually quite like. So this is one of 2 examples. Now, one thing to point out is you might see some corruption around the edges of the screen. This is because the drawing always works in 8 by 8 pixel blocks. So when it's sort of offset by a quarter or half a tile, it can't draw in those positions. The intention is that any final game would have basically a border of 2/3 of a tile on this system to fill in over those gaps. So it's not a bug that is appearing there. It's an intentional limitation, and to say it's just not part of this example to actually hide that with a proper border. Anyway, that's the example we're going to be looking at today. So let's go over to our code and let's take a peek. So here is the code. So the example is ZXM MaxTile mid. This is the drawing example that's showing the moving objects around the screen. This is the actual tile drawing routine. Now, MaxTile is very complicated. There's multiple parts to it. There's the example, there's the multi-platform code, and there's the platform-specific code. And it's only the platform-specific code we're looking at today. There's other tutorials on how the multi-platform code works out the scrolling and moves the simulated sprite objects around the screen. The point I'm making is if all of that's too complex for you, then what this is here is basically a routine that will draw a single tile to the screen, and it's been reasonably optimized and does things like Xflip and Yflip. So this might be something that you can take apart and use in your own code, even if the rest of MaxTile is too much for you. I would fully understand if that was the case. Okay, so MaxTile on this system uses a series of caches. These are 256 bytes. I've spaced them out a little bit during testing just in case there are any bugs, basically. But the screen is drawn in 3/3, and the reason for that is that it doesn't use a double buffer on any system, and so it caches the draws for each of the thirds. The intention being that if we split the screen into thirds, maybe we can redraw as the screen is CRT beam is redrawing and reduce the flicker that way. But generally, as I say, it's split into 3 buffers unless we enable the double buffered routine, which will expect a double buffer to be functioning. We'll redraw the entire screen every frame. There is no double buffer in this example, so if we enable that, we will get a flickery display. And if we just run that here, you'll see that. So you can see now we've got flickering there because we've got the double buffer isn't actually in function, and so you know, we should be changing the screen destinations and flipping between 2 buffers, but that isn't implemented in today's example. Now, one thing that I'm going to point out is we've got this thing called screen base here, and on other systems that is a VRAM destination. On this system, it's not. It's actually a Y and X coordinate, and the reason for that is we're doing page flip. We're flipping in the banks into system memory. We're using layer 2, which is the 256 color mode, and we're splitting it into 6 banks and paging one of those into the ROM area from 200 to 3FFF. And the reason we're doing that is to keep the low memory area available, because we can page RAM into there and then we can use interrupt mode 1. So that's why I'm doing things this way. I find it far more suitable for the kind of games I want to make. So there we go. So we're defining the size of the screen. It's 256 pixels by 192 in all systems. We work in logical units. That means pairs of pixels. So that's just something there. Now, there's some code for lookup tables here, color lookup tables. That isn't going to be used by today's example because I've disabled the 4 color mode. The 4 color LUT is only for converting 4 colors to 256 colors. We don't need it for today's example. So that's spare for next week, so to speak. So if we go down to the bottom of our code here, here are the definitions of the patterns for the 256 color mode. So there's a few different kinds of fill of tile within this example. So we have solid fill tiles like those, which use 2 bytes repeated every line, and then we have double height ones, and then we have regular ones, and we have a GIF capture routine, which is messing up when it's resizing GIFs. Which that magenta there, that's the GIF software. That's not actually what the example does. Anyway. So we've spaced things out here because, as I say, each of these tiles is 64 bytes, which is huge. Now, MaxTile was designed for 16-byte tiles, which is 4 colors for the Amstrad CPC and the like. And I'd say I actually do like that kind of style. I like the limited effect, and Chibi Akuma's, the characters were all designed as 4-color characters, you see, and so I do like that style of things. But anyway, we are using 256 colors today, so these huge 64 byte tiles here, and we're aligning things there, so the first tile of the background example is in the correct memory address there. So that's all we're looking at. The rest of the code I've discussed in other tutorials. Please see the MaxTile tutorials for how the multi-platform code and the simulated sprites are drawn. What we're going to look at today is these drawing routines here. So the first thing we've got here is a fake get screen pos routine. Now usually this calculates the VRAM destination on the system. On this system it simply moves B and C into H and L, but it converts them to pixels first. B and C are used for other purposes during the drawing of code. So for compatibility with the multi-platform code, I've had to move them into H and L at this point. Now, and that is one other thing I should have just said is we were actually turning on the screen, this layer 2 screen here. We've got all these next wedges here that basically set the screen up and its initial position here. So that's just turning it on, and we're turning on the speedy mode as well because we like the speed. So the multi-platform code itself will calculate the size of the tile map, and it will basically test each tile to see if it needs to be drawn. Now with MaxTile, unlike MinTile, each tile uses 2 bytes of the memory. Now one of those bits is actually an update bit. If the bottom bit, the least significant bit of those 2 bytes, is a 0, this tile doesn't need redrawing to the screen. It's not been changed or overwritten or anything, so we don't need to redraw it. Now, if we get to the draw tile routine, then that bit must have been set to 1. Otherwise, the tile map routine wouldn't actually call this. So we must know that that bit was a 1. And the other thing is that we did a shifting operation to remove the bit and test it. And so that bit has actually been removed at this point. And so we're shifting left again and then writing back. And that's to put a 0 back into the place where the 1 previously was. So here we're actually flagging the tile is drawn because we're about to draw it. Now BC here is actually pointing to the source tile map, so that's why we're writing back there. Now what we're then going to do is we're going to test what is now bit 0, but it was previously bit 1, and this is the program bit. Now these routines basically work as a bit of a binary tree. The intention is to draw the most common tile as fast as possible. Now that is an unflipped non-special tile. So if the program bit is 0, we're assuming it's unflipped. If the program bit is 1, it's something else. It could be flipped, it could be a fill tile, it could be anything, but the most common one is unflipped, so that's the one we get to first, and that's what we've got here. Now the format of the tiles, basically the bottom 4 bits, these bits here, are the update flag, the program flag, and then the X and Y flip and other options like that. These bits here are the least significant bits of the tile number, and the next byte, the high byte of the 16-bit pair, is also the tile number, and that's because if we were using 4 colors 16 bytes per tile, we would have effectively multiplied the tile number already by 16, saving us some time. However, in this case we need 6 to multiply by 64, so we've not done enough. So we're loading the second byte of the tile number in here into H, and then we're effectively multiplying by 64 by doing some shifts here. Okay, so we've now got our tile offset. What we're now going to do is add the base. Now D and D are actually pointing to the base of the tile patterns that are going to be used to draw to the screen. So here we're adding H and L to that base here, and then we're actually moving this into the stack pointer. We're using stack misused during this code. This is where we use the stack pointer for, in these cases, for reading from memory. So we can't use any pushes and pops for storing and restoring data, and we can't use any calls during these routines. Now what we're doing next is we are banking in the correct bank of the VRAM here into that 2000 to 3FFF range here, and that's what we're doing here. And we are also setting H and L to the VRAM destination, so they're now a true VRAM destination. So that's what's happening there. We've now paged in that correct bank, and HL point to our VRAM destination. So all we need to do now is we need to do 8 lines, and we need to do 8 bytes per line. So we're going to use L, and we're going to use L effectively in the shadow registers here as our line count. And then we're going to do 1 line as a sort of unwrapped loop. We could have a loop counter here as well, but for convenience, it's not so big. I like to try and keep things fast, so we've got a bit of an unwrapped loop here for each line. So we are reading in 2 bytes by popping them. Now, these are 2 source pattern bytes, and then we're writing them to the screen. Inking moving across the screen as we do all of the 8 pixels. Now once we've done a line, we move back to the far left by subtracting 7 from L. We then increment H, we're moving down one line. Then we've got to check and see if we've basically gone over the end of this range of paged in memory, and if we have, we're paging in the next bank. We know that the next bank will be required, we don't need to recalculate the bank number, but we do have to do that if we're if we've gone down over a bank. The only other option would be to require the tiles to be drawn on 8x8 pixel boundaries. I do that on some systems, but on this system that would have felt excessive because it's a very powerful system. It's not really comparable to most 8-bit systems. It's more like a 16-bit system in terms of performance. So it didn't feel appropriate to limit to 8x8 pixel boundaries here. So that's why we're doing that. And then we're just repeating until our L counter is done. So we're jumping back up here and repeating each time. Now at the very start of our code, we backed up the H component of the HL VRAM destination, and here we're just restoring it. And so when we return to the calling routine via this jump, H and L point to the starting memory address, because that calling routine will move the HL destination across the screen to draw the next tile. So that's the most simple tile drawing routine. Now in the case that we need something a bit more complicated, it's this advanced routine that will handle the job. So here what we're doing is we're checking to see the next 2 bits here. Now these are the X and Y flip bits. Now if both of these are 0, this actually doesn't mean any kind of flipping. This means that we're using some kind of custom tile. These are the special routines that have a special functionality. In the case of the example we've got here, transparency, double height, or solid fill. So we'll see those in a moment. Now what we're doing here is we're clearing the update bit again. Here we have to do this at this point because we've basically changed the source byte here and we didn't run the code that was there before. Now in this case what we're going to do is we're then going to effectively calculate the tile number here. If we've got to this point, we're doing either Xflip, Yflip, or X and Y flip. So calculating the tile number we can do. We know what the format is. We know we need to multiply by 64. So these are the same tiles as before. Now we're loading our line count again here, but then what we need to do next depends on if we're doing Xflip, Yflip, or XY flip. So here we're checking the Yflip bit, and if that's not set, then we must just be doing Xflip. And in that case, what we want to do is we want to select our VRAM destination here, but then we want to move to the right-hand side of our tile and work backwards. So we're reading in the source data forwards and drawing it to the screen backwards, and this effectively Xflips the sprite. So very straightforward there. That's what we're doing here. So once we've done that, we're then basically just moving through our tile data exactly as before, popping them, drawing them to the screen, and we're repeating it until we're done. So the only difference with this and the normal one is that we are moving to the right-hand side, and instead of inking L, we're decrementing L after each byte has been drawn. So apart from that, you're basically the same. Now that's the Xflip routine. The Yflip routine here. Here it is. This actually also handles the XY flip. There's a branch here to do XY flip, but the starting procedure is the same in both cases. We've already got our tile number here, but what we need to do is we need to calculate the VRAM destination. And in the same way as we went from right to left when we did Xflip, we go from bottom to top if we're doing some kind of Y flip, and that's what we're doing here. So we're adding 7 to the line number basically when we calculate the VRAM destination here, and that's so that we start at the bottom of the tile and we move upwards. So that's what we do there, and then we decide if we're going to do an Xflip and a Y flip or just a Y flip. We've actually ended up with a second copy of that code there. It's a copy paste error. I apologize for that. We'll just delete that. And then what we're doing here is we're basically just drawing, in this case, un-Xflipped, Y-flipped. So we're going from left to right, drawing the lines as before. And we're going up the screen this time by decrementing H rather than incrementing it. And then here we're just recalculating if we've gone under the current bank, because we're going up the screen this time, not down. So that's what's happening there. Again, pretty straightforward, pretty similar to the original one. And then the final one is X and Y flip, and all we do is we do both things. So we've already calculated the bottom line, and this time we start from right to left, drawing the pixels to the screen. So there we go. So that's how we do our X and our Y flip. Pretty straightforward. So those are the flipped tiles, and that's so you could unwrap even more, and you could sort of have no loop count for the Y lines, but on this system that would have created an awful lot of code. Felt excessive for such a fast system. Okay, now custom tiles are the things like the filled tiles, transparent tiles, and the double height tiles. So what we're doing here again is clearing the update bit. We're then deciding basically we're taking these 2 bits are a part of the tile number, but these 2 bits are actually the custom program type. So that's what we're looking at here. So we're taking those 2 bits and we're deciding if we're doing a filled tile, a solid fill tile, a transparent tile or an empty tile, or a double height tile. Now if we get here, we're doing a double height tile. These use the same source pattern data, but they double the height. Now this can be used for a cute effect. You can see it looks a bit like a metal slug. Maybe that used to like stretching its tiles, but really it was designed as a memory saving thing. By doubling the height of the tiles, we can use pattern data, and we can use half the pattern data to fill an area, and it still looks pretty nice. So this is something I did in my Suck Hunt game for the introduction. Didn't have enough memory, wanted to do something with a certain number of tiles. Half the height of the tiles, half the height requirements of the memory. Very straightforward, and it looked good still. So that's what we're doing here. So instead of multiplying by 64, we're multiplying by 32. Also, our calculations are different because we're using fewer bits of the source source address, and they aren't as conveniently optimized now because, as I say, we're in the weeds, so to speak, with regards to the custom code. Less frequently run, less efficient. So that's why. But the drawing routine is basically very straightforward. So all we're doing here is we're reading each byte from the source pattern, and we're drawing it to 2 consecutive lines. So you can see we're incrementing H to move down a line, decrementing H to move back up a line, after drawing each byte from the source twice to the screen. And then once we've done our pairs of lines, we're moving down the VRAM here, and we're doing our loop count. But our loop count is this time only 4, because we're doing pairs of lines 4 times to do the full 8 lines. Now, actually, because we're using logical units for our coordinates, these are pairs of pixels, so we don't need to actually worry about going over the boundaries quite conveniently mid-draw here, because we're always moving in pairs of pixels anyway. A bit of a lucky coincidence there. So that's the double height. Here we have the fill. So the fill tiles, again, are pretty straightforward. Basically, these only use 2 source bytes of data though. So again, we're paging in our VRAM here and calculating our source data here, but all we do here is we basically just pop a single pair of bytes, and we do an entire line with the first byte, move down 1 line, and we do the next line with the second byte, and then we recalculate our VRAM, and again we repeat that 4 times because we're doing pairs of lines with a single byte. You can see these are the kind of, those tiles there are the filled tiles. This is designed for speed, because if a lot of your screen is black, you don't want to be loading in lots of source bytes of data to fill your background. So if your background's black or color 1 or color 2, you use something a bit quicker, and this is going to be pretty much as quick as you can get, unless you're clearing the screen every time at least. So that's what that was designed for. But as I say, it was filling tiles where there's no detail needed is fast. So that's what we've done. The final tile kind is empty tiles. Now these are 2 things: areas that simply have no data drawn. That Yorita character there, there's nothing drawn around its feet, so we don't have any tile data there, and those are empty tiles. Now empty tiles, the second byte is basically 255, so we're comparing that by inking A. If A was 255, it will now be 0, so we can now do a 0 branch here, and in that case we simply flip to the shadow registers and return. But if that tile number isn't 255, then we're doing a transparent tile. Now these use the same source pattern data, so again we're multiplying the tile number by 64, calculating our source data as before, but these use a very crude transparency type, which is byte comparison transparency. This is used by Chibi Akumas. I think it looks quite fun. We just fire up the example again here. So you can see that character moving down there and has now gone off the screen. The black areas of the tile there aren't being drawn to the screen. It keeps escaping from me. Aren't being drawn to the screen. And so this is a byte 0 transparency. Now in this case actually a byte is an entire pixel. On other systems it was often 4 pixels, which gave the characters a kind of black border unintentionally. But I actually quite like that because this game was always a cartoon game. Anyway, all we do to achieve this is we are popping our source data, but before we draw it to the screen, we're actually comparing it to our comparison byte, which in this case is a 0 byte. And if it matches, we don't draw it, and we just move along. So this is obviously going to be quite a bit slower. That was the case in Chibi Akumas, again, which use this kind of transparency, which is why you use it as little as possible. With Chibi Akumas, the player sprite was transparent. The background sprite, the enemy sprites, generally I don't think were. I'm forgetting now, it's so long ago. I don't think maybe some of them were, but most of them weren't. The background objects certainly weren't. So you just use this as sparingly as little as you can. Now, the reason I'm loading the accumulator with the comparison byte here is because maybe you don't want to use byte 0 as transparency. Maybe you want to use a different value. And so by having an easily modifiable value here, maybe by self-modifying code, you can change the comparison. But as I say, apart from that, this drawing routine is basically the same as the first one. All of these are sort of derivatives and alternate versions of the original one. So there we go. So that's the example today. As I say, go to my website, download the source code, the build scripts, and have a go with it. And even if it's too complicated for you, maybe just use some bits of the tile drawing routines. Even if you just take some inspiration from them. You know, often things, I often find it's easier to write your own things that you understand rather than the things that you use other people's code that you don't. But as I say, maybe you'll see some things in here that you find nice ways of doing things, you know, unwrapped loops and using stack misuse, and maybe you want to use those, or maybe you'll think all of my ideas were stupid and you think far better ones. Well, if I've helped you think of something good, then great. As I say, you can look at other people's code and see, and it can help you learn, help you realize better ways that you want to do things. And I always think that's a good thing. Anyway, I hope you've enjoyed what you've seen today. Stick around though, we'll be looking at that full color version for the Spectrum next time. Thanks for watching, and goodbye.